talk is 100G single lambda transceiver. I know there are some presentation on single lambda on the web, and I will concentrate on some practicality of it, namely how to use it, what some real parameters. So hopefully this will give you some insight into a single lambda, to say the least. First time a user usually has some trouble because there is some difference in between this single lambda and the other type in 100G family. So basically, I will talk about those three things. First of all, I explain briefly what the single lambda is. I use a single lambda abbreviation, and then talk a little about their performance and some functions, and third, and the things to watch out when you operate the single lambda in a switch environment, for instance. So what is single lambda? Single lambda usually has three flavors: the DR1, FR1, and LR1 in the QSFPDD housing, and can reach up to 500 meter, 2 kilometer, and 10 kilometer single mode respectively. And it's a hot pluggable QSFP28 and with the duplex LC optical interface. Now here comes the little complexity here. On the host side is always 4 channels or 25 gigabit per second NRC on the host side. But on the line side, the DSP inside the transceiver will convert it into PAM4 signal. And the aggregate weight, there is converted into 53 gigabaud, which is equivalent to 100 gigabits per second on the line side. And the power is always 4.5 watts. And the spec, it can be found in a document called 100G FR Technical Specification Revision 2. Okay. So let me move on just a little bit. And so on a 100G CWDM4, that's how it is. So you can see on the left side is all 25G, 4 channels of 25G NRC coming in to CDR. And fourth, I have to emphasize 4 pairs of CDR and 4 pairs of laser driver into laser. The laser can be EML or CWDM or DRB, that is, and then go through a MUX. And then on the receiver side, there is a DMARC, there is a PIN, the TIA, and limiting M, and CDR, and going back to the whole side. So on the counts, I just roughly put down the number of components, major components here for comparison with the next page. So again, on the electric side is COWI4, 25G NRC. On the line side, now it becomes, it not become, because it's still CWDM, I'm sorry, I was thinking about single lambda, it's still 25G NRC, it's no difference. Okay, the format remains the same. And the next page shows the single lambda, and again, on the host side is 25G NRC 4 channels, but it goes into a DSP with the conversion ratio of 4:1. So it converts into 53 gigabaud PAM4, which is equivalent to 106 gigabits per second. And again, it's only one laser, so we call it single lambda, coming back into a pin detector and going through a TIA and LR. Be careful. I put red on here because now the difference in components is linear. The laser driver has to be pre-linear, so as a TIA. And since the signal format is PAM4, everything has to be linear, as opposed to NRC. So then coming back to the second half of the DSP, going back to the host. So you can see the component count here is a little bit less now. And now, but you don't expect the cost to go down as the ratio of the component counts, right? Simply because the DSP is pretty expensive. So it outweighs everything. But you have a little bit saving, basically, in terms of material. It's about 55% of the CWDM4. But however, the volume of the single lambda is still pretty low. There's no comparison to the 100G CWDM4. So in fact, the price needs to be driven low when there is more deployment. So people say, in 2 years, maybe 3 years, the volume will be up there. So as the price will come down. So much for the configuration. Yeah. So let me go to the next page. We give you some hands-on feeling about the performance of the single lambda. I intend to use this because it's so different from the NRC. When you operate a PAM4, there is always error, just keep in mind. So you can see here on this side, there's a bit error rate. Here's the input power. You can see this, however, the spec, the IEEE spec is right here as 2 to the e to the -4. And anything below should be okay, because when you turn on the KP4 FEC in the host, not in the host, in the DFP, and the bit error rates would be driven down to less than 1 e to the -15, which basically is error-free. Okay. So, but if you don't do the fan, but you have this curve, and it should be okay. So if you see this, you should feel good, because it is supposed what it is. And when operating in PAM4, there are parameter change. Keep in mind, the transmitter that we usually familiar with, TDP, that's a transmitter dispersion penalty. Now it becomes T.Q. T.Q, the less the better. So the maximum is about 3.5 dB. So remember, the less is better. And also there's one more parameter very important, which is RLM, has a value from 0 to 1, defines the vertical linearity of the PAM4 signal of all the levels. Okay, remember, anything in PAM4 has to have reference to 4 different levels or 3 different lines. So that's why it is very challenging to keep it linear. And also, I like to point out the sensitivity is not the same way you look at it on the NRC. And I put up one slide behind this one to explain what it is. We call it sensitivity mass. So I show you a typical data sheet on the single lambda, right? There's a data sheet here. This on the receiver data sheet, transmitter data sheet. Now I highlight the ones which are very important in sensitivity calculation. First one is this, we call it T.Q. It's kind of equivalent to extension ratio, but with the PAM4, which has the outer and inner eye. So that's one. And second one is the equation. This equation sometimes is put in the notes. Sometimes it's put in the table itself. Now, and I want to explore this just a little bit for the sake of explaining its function. So I plot that out. This curve is called a receiver sensitivity mass, right? It's a mass. So how is it plotted out? I list 4 points. With these 4 points, you are able to plot it out. The point A is maximum sensitivity, right? Here is sensitivity, OMA. So here's the maximum sensitivity, which means it is the lowest level of the optical input power, right? That's what we call maximum sensitivity. A here is simply from this equation. You can see it's minus 3.9. Okay, so this is your starting point. This is the maximum sensitivity right here, right here. Okay, that's another point is B. Point B is called minimum sensitivity. Is the other side. Is the minimum sensitivity, which is, again, look back onto this equation. CQ, we call it CQ, minus 5.3 is given by the supplier. So you put it in CQ minus 5.3. Now CQ, that's for the receiver, but on this calculation is equivalent to theta Q on the transmitter. You can see CQ or theta Q. So we can use this theta Q here, 3.4. So you plug in the 3.4 in place of the CQ, 3.4 dB minus 5.3 dBm, which is given in this equation. You come up with so-called minimum sensitivity, minus 1.9 dBm. So which is here. You can look at the plot here, right? Minus 1.9 here. Here's the second point. Now the third point would be C here, right? So because you need to know maximum theta Q. Maximum theta Q is the same as this, right? You go look back on the transmitter spec. Maximum theta Q is 3.4. So here's 3.4. So here's 3.4. Because you need this one to plug it as well, right? And then the last point is the intercept point, this point, D. I call it point D, which is the difference. You can see, right? So basically this curve is called from here to here. It's all the supplier would give you a guarantee of this sensitivity, which is minus 3.9 dBm from here, from the OMA minus 3.9 with the theta Q from 0 to 1.4. Basically, that's what it says. But after this point, it should be 1-to-1 relationship, right? So you have, for instance, from the theta Q from 1.4 to 3.4, which is 2 dB difference. And you shall have the input power on OMA 2 dB from this point to this point, right? So basically here's flat, here is linear, 1-to-1. That's all it means, this sensitivity mass. So you can see the intercept point D is equal to 3.4 minus 2 dB, right? Because it's 2 dB from here to here. So you end up with 1.4 dB, right? Here is 1.4 dB. So with those 4 points, you'll be able to plug this out. And the other meaning is anything here, now we call it is a mass, not as a line, a mass, right? Anything beyond this is guaranteed the performance here on the upper side. Okay, it's called a mass. Okay, so let me go on to the next one, which is the function of the single lambda. Now, I was in the single lambda development team, right? In there, we deal with always work with the DFP, and those the function the DSP offer to the user. So you can turn the host. You know that there is a table, logical table here, but this table was developed before the CMOS 4.0 was released. So as in fact, in the early days, this table is embedded into some user EEPROM. So for the user to use. But now, if you look at the page 13 and page 14 of CMOS 4.0, most of the function here is included. So that's why you need CMOS 4.0 to operate. Otherwise, there are functions you cannot touch. Yeah. So you can see here all the functions. And also, I want to remind you, in the extended ID field, which is universal to almost all transceivers, right? In page 0, 192 byte, which is called identify the extended specification compliance code for the transceiver. In this byte, and it defines the single lambda family in this bytes, right? I put it in, just make sure you realize this. It calls out no FEC, no FCC, no FEC. That's on the whole side. When you look into the document of SFF 8024, it defines what the host would do and what the optical side, the light side would do, the transceiver would do. In there are lots of information, and you need to read that table very carefully. Otherwise, we have customers, sometimes they turn on the FEC on the host, and it just doesn't work. It doesn't, the traffic doesn't pass, right? Because that doesn't go with traffic. So if you do that, there is no link. This is the very usual error sometimes made by the user when they first turn on the single lambda. I put it up just for a caution. Look at this and make sure you operate the parts correctly. The last slide, I just want to put it up, and there are two different ways to do this breakout. So you can see, right, 400G QSFPDD DR4 is a perfect interface to the single lambda DR, right? You can see why DR4 and DR. So basically, you have two interfaces. Either you have the MPO, you plug it in, MPO, and then you use the cable to split into 4 different LCs to plug into here. Since the format, everything is the same, it's a PAM4 on the light side, and it should operate perfectly. And then there is another option called SN connector. You can plug it in. The SN connector on the transceiver side looks like this. So you don't need any breakout cable. You just use this cable, plug it in, and because on the other side is LC anyway, LC. So there are 2 ways to interface this in the breakout options. As I just pointed out, there are people are using this right now. Just be aware. So that's all my presentation, my sharing with you, and I can ask some question if there's any. Let me check. What percentage of customers are using MPO versus SM? Haha, very good question. I see some tier 1 customer using it, and I don't know the percentage, but I would think the percentage is not very high because you can see, right, on, let me close this a little bit. On the transceiver, it has to be designed like this. So this one is much longer in terms of physical length than the usual 400G DD. So from, you can see, right, to accommodate this plug-in here. So there is a cost to redesign this DR4. But I have seen several tier 1 customers in the big data center, they used this already last year. So I think they developed this requirement about 3 years ago. So you can see they were preparing for this option. And now I think you need to find the compatible transceiver in order to use this. Yeah, that's all I want to say. Question number 2. So all the single lambda product, irrespectively of the supplier, have a FEC inside them. Yes, truly. For any PAM4 on the line side, it must have FEC. It's a KP4, so it's in the standard. Yeah, so that's correct. There's a third question: is DR going to be dominant single lambda rich? How much adoption is FR getting? Right. Well, the application is a little bit different, right? FR, you talk about some distance, so maybe like 2 kilometers and so forth. And it's not as dense anymore. And then also you can see there is a mux inside, right? In order to break it through, you need optical mux inside your breakout cable. That's the price you have to pay, right? So I think DR1 definitely with 400G DR4 should be in the most dense area because it's much easier to interface. So for maybe across from one end of the data center to the other one, probably you would use more complicated solution like a FR4 or even LR4. Yeah. Okay, so there's one more question. Does 400G DR4 has 4 wavelengths? No, they are all 1310. So they are, see that's a design for DR1, right? All DR1 has a 1310, right? Single lambda. So as a DR4. So DR4, they have identical channels, 4 of them, but with the 1310, yeah. So they can directly interface with DR1. That's the beauty of DR4 to DR1, I believe. Yeah. That's all the time we have. And so I pass this back to Priya. Thank you.